Hello everyone and welcome to another video. So today I'd like to continue our discussion on linear algebra by investigating the concepts of row and column space of a matrix, which is going to lead to a discussion on linear independence, which is very closely related to what's known as the matrix rank or the rank of a matrix. So with that being said, why don't we just jump right into it? Let's consider a matrix that looks like this, right? In the sense that it has m rows and n columns. Okay, so it's just your standard matrix. You can lay it out as a bunch of entries just like this. Or what's going to be very helpful for the discussion today is to think about this matrix being comprised of a set of, for example, rows to start with. Like, let's look at this first row right here and call this row 1. And then you have another row right here. Let's call this row 2. And as you can see, you can think about this matrix A as nothing more than a bunch of row vectors stacked one on top of the other, right? R1, R2, all the way down to Rm, because we have m rows in this matrix, right? The alternative way you could potentially think about this, right, is instead of thinking about rows, you can think about them as columns. Like you could grab this first column here in red, right? And then a second column right next to it, etc., etc., etc. And you could think about that matrix being stacked up as column 1 horizontally concatenated with column 2 all the way down to horizontally concatenated with column n, right? Because there are n columns in this matrix, right? So with that framework in mind, we can think about a matrix as nothing more than a bunch of vectors stacked up either as rows vertically or columns stacked up horizontally, okay? So this leads to the discussion of what's known as the row space of a matrix. So the definition of the row space is the row space of a matrix A is the span of all of its row vectors. So in other words, what that means is you take all of these rows of the vector and you try to create linear combinations of them, right? So in other words, this is a set of all possible linear combinations of the row R1, R2, Rm, right? And just to refresh everyone's memory, what that looks like is you have some coefficient, let's call it maybe, some scalar, x1, multiplied by the first row, plus x2 multiplied by the second row, plus some plus all the way down to xn multiplied by the mth row. Sorry, that should be m, right? So this is a linear combination of all of these rows, R1, R2, all the way to Rm, right? Because all I'm doing is I'm adding them together with a potential scalar scaling of each one of these rows before adding them together, right? This is the linear combination of all the rows. So every single possible value of this makes up now the row space. So you can change x1, x2, xm to be anything you want, and all of those possible locations is what's known as the row space of this matrix. So all you're doing again is just combining these rows R1, R2, etc., together, right? That defines the row space. So the reason this is useful, I always like to think about, right now this definition sounds somewhat abstract. It helps if we think about a particular set of equations. So the row space, I always find it very useful to think about if we have this very standard kind of matrix equation where you have some matrix A and you're going to left multiply with a row vector, let's call it x, to get some new vector B. So this is basically B equals x times A, right? And again, just to lay out the dimensions of this, x here is going to be a row vector with m elements, right? x1, x2, xm. And as we said, we can think about A as being nothing more than a bunch of row vectors, row 1, 2, all the way down to m, stacked vertically on top of each other, right? So if you do this matrix multiplication, and again, just to refresh your memory, feel free to check out our previous video where we discussed, elementary matrix operations. But I'll leave this as an exercise to you to show that, you know what? This actually turns into this, right? So B is just this expression on the right, where if you compare this with what we just discussed over here, it's the same thing, right? So what we see here is if you have a matrix A and you are going to left multiply with a row vector x, what you're doing is you are creating a linear combination of the rows of the matrix A, right? Because the resulting output of this function or this transformation or however you want to think about it, right? This B vector is now comprised of a linear combination of the rows of the matrix A, right? You can see B is nothing more than you take the row 1, row 2, all the way down to row m, and you are scaling each one of these by these coefficients x1, x2, all the way to xm, and you're then adding them all together, right? So what ends up happening is the only solutions or the only outputs B that you get have to be in the row space of the matrix A, right? Because it's nothing more than a combination of all of the rows of the matrix A, okay? Great. So that's what the idea is. This is why row space is helpful, is because if you ever have an equation like this, right, and you want to ask yourself something like, is it possible to solve this equation, right? Let's say someone gives you the matrix A, someone gives you the matrix B, and you need to find these x values that make the left-hand side equal to the right-hand side. Well, the only way that's going to happen, right, is if B is actually in the row space of A, right? Because B has to be made up of a linear combination of the rows of the matrix A, right? Okay, so that's why it's helpful. Let's maybe go to a concrete example to look at what this looks like. So let's consider you got a matrix A that looks like this, right? It's just a bunch of these numbers I kind of picked out of thin air, right? Now, if you remember our previous video where we discussed elementary row operations and this idea of reduced row echelon format, we saw that elementary row operations, they don't change the fundamental nature of the rows of the matrix, right? So what this means is that we can reduce or place this A matrix in a row echelon or a reduced row echelon format, and we are not actually going to change the row space of the matrix, right? We won't change that fundamental quality about it. So what I'm going to do now is I'm going to row reduce this original matrix, and you're going to end up with this, right? You see we have pivot here, 0 down here. That's great. What this basically tells us is we are looking for these first two rows, right? Because these two rows are clearly the non-zero rows, right? You got one row of zeros down here. So all possible combinations of the rows of A are made up by these first two, right? Because you can clearly see these two row vectors by construction, they are not pointing in the same direction. They're what's called linearly independent, right? We're going to touch on that a little bit later in this discussion. But these two rows, basically the rows in the reduced echelon format that are non-zero, they comprise a basis for the row space. So in other words, all I have to do is pull off this row and this row, right? Maybe let's call this R1 and R2, right? And now what we have is that the row space of the matrix A, also maybe I'm going to write this here as row SP of A. All this means is this is the row space of the matrix A, right? It's basically the subspace of the span of these two vectors R1 and R2. In other words, it can be comprised of any linear combination of R1 and R2, gets you the same space description as any possible linear combination of all of the rows of the matrix A, right? We just see that this is a basis in the sense that it is the minimal set of vectors that I need to describe this subspace, right? So these two vectors are, as you can see, I just pull off this first non-zero row, that's the first vector, and then the second non-zero row, that's the second vector, right? So again, what we see here is that, coming to this equation, right? If you have an equation like this, all of these B vectors are going to lie as a linear combination of these two vectors, R1 and R2, right? They have to lie in the space spanned by these two vectors, okay? So I think the easiest thing to do is maybe let's go to Matlab and visualize all this, because we see we actually are in a nice situation where I think we can actually plot this in 3 dimensions, right? This row vector R1, it's just a 3-dimensional vector, right? It's pointing in the direction 1, 2, 0. The second vector is pointing in the direction 0, 0, 1. Right? So I basically have one vector here, I've got another vector pointing somewhere else, and the space spanned by that is basically any linear combination of these two vectors. But instead of me just kind of waving my arms around, let's go over to Matlab and actually look at that. Alright, so here we are in Matlab, and I've just got a really simple script to help illustrate these spaces we're talking about. So here I'm just going to define the matrix A, and then what I'm going to do is I'm going to define these two basis vectors that we claimed describe the row space of that matrix A. So again, this is just what we had on the board earlier, R1 and R2, okay? So what I'd like to do is, let's first go ahead and just plot those two vectors R1 and R2, right, in 3-dimensional space. So let me just go and run this right now. And I'll pull this plot up here, and we can see what we've got here is, whoops, sorry, I don't want to translate, I want to rotate this. Let me hold on, let me fix this guy. Let me go ahead and click the rotate button. Okay, now here we go, we can rotate, and we see we got two vectors. R1 and R2 are these green and red vectors, and what we're seeing here is that these two vectors, right, they describe a space, a two-dimensional space that's embedded in the three-dimensional larger subspace, right? So the row space of the matrix A, we claim, is now spanned by all linear combinations of this red and green vector, and as we can see, that defines a plane in three-dimensional space, right? It defines a two-dimensional subspace, right? Okay, so that's great. We claim that now that's the row space of the matrix A. What I'm going to now do is I'm going to randomly generate 100 different vectors, where the first thing I'm going to do is I'm just going to pick a random set of coefficients or a random x vector. Let me put a breakpoint in here and I'll continue running. Okay, so we see x is, this is just some random vector, right? It's a random 3-element row vector. You can think about this as the coefficients of now the first coefficient of row 1, right? Because you can see right here, I'm just going to do my equation b equals x times a, right? So there's this much of row 1, there's this much of row 2, and there's this much of row 3 of these matrices put together to make a linear combination, which is now going to make this other vector b, right? And I'll just go ahead and evaluate that as well. So again, b is now this other random vector, right? And now what we claim, right, is that this vector b, it will lie within the subspace spanned by R1 and R2, right? So if I plot this vector b as just a thin blue arrow, let me go ahead and hit F10 here and bring up the picture again, right? Aha, there you are, right? You see we get this blue vector, which does indeed lie within the plane spanned by the red and the green vector, right? And in fact, all I'm going to do now is just do this another 99 times to just get a whole bunch of random b vectors and continue plotting them. So let me go ahead and put a breakpoint down here, and I'm going to let the rest of this thing run and pull up the picture again, and yes, we see that all of these blue vectors do indeed lie in the space spanned by the red and the green vector. Now, in fact, the scaling is a little bit tricky here. It's not the most visually pleasing picture. That's because all of these vectors are not unit vectors, and again, we really should normalize them, because all we care about, right, is the dimension, or excuse me, the direction of the vectors. I don't care about the magnitude. So in other words, I should just go ahead and scale all of these to be unit vectors, right? So everything fits in a nice picture. I'm not going to change the description of any of these subspaces, right? I'm just changing how long the vectors are, so I don't have these scaling problems, right? So let me go ahead and add those 3 lines where all I'm doing is making them unit vectors now, and rerun this. And now this should look a lot better, right? And again, we see all of these random blue vectors, which are the result of the b equals xa operation. All of those blue vectors lie in the space or the plane spanned by the red and the green vector, right? Perfect. So there we go. That's a good visualization. I hope that we see that all we're talking about now is that the row space of this matrix, in this particular case, it's actually a two-dimensional subspace embedded in this higher three-dimensional subspace. All right, so that was a discussion on the row space of the matrix. So now let's turn our attention to what the column space of a matrix is, and it's very, very similar. In fact, I've left most of the board untouched from our row space discussion, and now we can just change anywhere we saw the word row to basically be column. So now the column space of the matrix is basically the column space of this matrix is the span of all of its column vectors. So in other words, it's just the set of all linear combinations of all of the combinations of the columns of the matrix A, right? So now we're looking at C1, C2, Cn. So this combination, and again, I apologize, it's got a little bit out of hand here, but all we're doing is taking the first column, adding some coefficient to it, or multiplying by some coefficient, and then adding to the second column, multiplied by some coefficient, adding to the nth column, multiplying by some coefficient xn, right? So this is the linear combination of all of the possible combinations of all of the columns of the matrix A, right? Okay, so let's come over here, and now I want to, again, let's make some modifications. So again, I want to replace this row, this word row with column. So the column space is useful if we now consider, instead, let's multiply on the other side. So let me just rearrange this. I'm going to put the x on the other side now. Okay, let me go ahead and write it like this. Okay, like this. So now what we're really talking about is I want to move this to the other side, and I want to write the matrix in terms of columns. So instead, what this line looks like is A now looks like C1, C2, Cn, right? And then the x vector is a x1, x2 all the way down to xn, right? Because there are n columns. So again, you get a linear combination which looks nothing more, I mean, it looks really, really similar, right? It's just x1 times c1 plus x2 times c2 plus plus xn times cn, which again, we see that this equation, the ax is equal to b, in this case, is really nothing more than saying b is a linear combination of the columns of the matrix A, right? Which again is the definition of the column space of the matrix, right? So again, I like this equation a little bit better. It physically makes a little more sense. I like to think about matrices in columns. But what this is basically saying, right, is that this vector b, the solution to this equation, b is equal to ax, right? This b has to lie within the column space of the matrix A in order for this to be possible, right? Okay, so again, we now want to ask ourselves, how do we go ahead and compute the column space of the matrix? So again, let's look at the same example we said earlier, right? This is our discussion on the row space, right? The only difference now is that the column space of a matrix does change under elementary row operations. So this statement is still true because this says the elementary row operations do not change the fundamental nature of the rows of the matrix, but it does change the column space. So the way we find the column space of the matrix is a little bit interesting. We still go ahead and row reduce the matrix, okay? But now let me erase all of this blue here because I want to draw your attention to another aspect of the row reduced form that is going to be helpful for computing the column space. So again, let me just go ahead and erase this blue, right? Okay, and I guess yeah, we can erase this blue comment because we know how to get the row space, but I don't want the row space, I want the column space at this point. So again, what we do here is you are going to go ahead, get the row reduced echelon form or a row echelon form. It doesn't matter either one. But what we're looking for now is we want to identify the pivots. Okay. So in fact, maybe I'll do this in a red color. Okay. So there's a pivot here and a pivot here. Okay. So we see that we have pivots in columns 1 and 3. Okay. So what we then do is we go back to the original matrix and we look at the first column and the third column. In other words, the column space of this matrix, so again, let's change this word here from row to column. The column space of A, which again also might be written as, let me write it as col space of A, right? It's the span of these two other vectors. I'm going to give them a different name. It's going to be C1 and C3, right? Right? Where C1 and C3 are actually the rows, the columns of the original matrix, which corresponds to pivots in the reduced matrix. So in this case, C1 is going to be 1, 9, 12, and C3 is going to be 0, -6, and -6. Okay, so let's go ahead and yeah, let me go ahead and erase some space over there on the board and maybe write down that procedure. Okay. Okay, so we see the procedure then to find the column space of A. It's a little bit more involved than the row space calculation, but not by much, right? Because all we have to do is you take this matrix A and you place it in some echelon form. That's either row echelon form or reduced row echelon form. Then all you have to do is identify which columns have pivots in the reduced matrix. And then you just go and look for the corresponding columns of the original matrix, and those form a basis for the column space of A. right? So again, just to come back to our example, right? You see here's our original matrix A. We put it in reduced form. We identify there are pivots in columns 1 and 3. So therefore, the columns of the original matrix 1 and 3 form a basis for the column space of the matrix A. Now, another way you could actually calculate this, which is actually interesting, is remember, right, that the column space was useful when we considered this equation, right? B is equal to AX, right? So let's just write that here. B is equal to AX, right? What happens if we, actually give me a little more space, sorry, I need a little more room here. B is equal to AX, okay, right? What if I transpose both sides of this? Okay, so we end up with, again, the right-hand side. Remember, you got to reverse the order and transpose this. So you go X transpose times A transpose, right? So we end up with this thing, right? This thing over here, now this is a row vector, right? Same thing with this X. This is a row vector. You know what? Let's just call these something else. I don't know. Why don't I call this thing... I don't know, how about instead of a bar, let's call this B wiggle for a row version of this. Let's call this X wiggle, and then this thing is now A transpose, right? Doesn't this look a whole heck of a lot like the row space discussion we had just a few minutes ago, right? So now we see that this B is now has to lie in the row space of A transpose. In other words, what you can think about here is that the column space of A, right? It's actually the same thing as the row space of A transpose, right? So here's another way you could do this. You could go and calculate A transpose, just basically transpose that thing, calculate the row space, and that gives us the column space. In fact, why don't we go ahead and do that just to show that it's the same thing, right? So let me make sure I got this right here. Okay, so here, let's go ahead and calculate A transpose, right? Which is really, really simple, right? You take A, and now we're just going to flip rows and columns. So now I got 1, 9, 12 across the top, and then you got 2, 18, 24 in the middle, and then you got 0, -6, -6, right? Okay. And now all I'm going to do is let's row reduce this thing, right? So let's go ahead and row reduce this A transpose matrix, right? So literally go run over to Mathematica or Matlab, whatever you want to do, place this thing in reduced row echelon form, and what you end up with is, let me see here if I can get this right, you get 1, 0, 3, 0, 1, 1, 0, 0, 0, right? Okay, so I can now find the row space of this matrix, right? A row space of A transpose. That was nothing more than the non-zero rows, right? So it's this row and this row, right? So we see that another description in our case is the span of these two vectors, right? So now we have the span of the vectors. Let me call this another two vectors. I don't know, what did I use in the notes here? Yes, so I think I called this like a D1. Maybe I should do this in purple, right? Because it's all purple. So here's D1 is this row, and this is the D2, right? So now we have, this is spanned by D1 and D2, right? Where in this case, D1, right, is just going to be, and I'm going to write them vertically, right, because I'm talking about column spaces. Sure, they're displayed here as rows, but these are the two vectors that I'm looking at, D1 and D2, right, is, D2 is 0, 1, 1, right? So we've got two sets of possible basis vectors here, right? So here's one set which describes the column space of A, right? It's these vectors, D1 and D2. The other one that we have here is these are also the column space, right? And we claim that these two sets of vectors describe the same subspaces, right? And again, you can see they're not numerically the same. They look like they may be pointing in, slightly different directions, but they should describe the exact same space, right? So this is an interesting discussion. maybe for the sake of completeness, you can also get by symmetrical analysis, right? Right now we're talking about the column space, but earlier we were looking at the row space. So I just want to make this row space of A is also equal to the column space of A transpose. Right? So again, if you were to run that analysis with our example over here, okay, so what do we have to do here? So let's go ahead and just compute the column space of A transpose, right? So to get the column space of a matrix, right, we have to go ahead and identify the pivots, right? So in this case, we see now in this case, there are pivots in columns 1 and 2, right? So that means this column 1 and this column 2 are also describing this space here, this column space of A transpose, which we said is the same thing as the row space of A. So again, just for completeness, let's go ahead and just say that this row space of the matrix A is also described by the span of these two columns here. And what did I call them here in the notes? Let's just call them a V1 and a V2, right? So this thing here is V1 and this is V2, right? So I just want to make sure that we have a whole set of descriptions here. So V1 is going to be 1, 2, 0, and V2 is going to be 9, 18, negative 6, okay? So we've got all of these. We should go to Matlab now and go make sure that when we plot all this using the same scheme that we had earlier, all of this checks out, okay? So yeah, let's do that. We have all these descriptions of all these different subspaces. We see how to compute them in various different ways. Let's go to Matlab and make sure that they all look kosher. All right, so here we are back at the same script. The only thing I've done is let's take a look at the row space first. That was the very last thing we computed on the board, right? Remember we computed this alternative description of the row space of the matrix A by computing actually the column space of A transpose, and we obtained these two vectors. So again, I've just added these two vectors here, V1 and V2, and I've added them to the plot here as a magenta and a cyan line. And then I'm just running through the exact same code. So tell you what, let's run this again and see what we end up with. And here's the picture. And as you can see, these dark lines, the green, red, magenta, and cyan lines are all in the same plane. So again, remember, the green and the red were our original basis vectors for the row space of the matrix. So the green and the red, unfortunately you can't see the green because the green is vector R1, which if you look at up here is actually pretty much the exact, it is the same vector as V1. So V1 has kind of overridden it, or it's hiding it, so that's why you can't see the green vector, but it's hidden underneath this magenta vector. So what you want to look at is the green and the magenta vector, right, were our original description of the plane, and now we have this magenta and cyan lines, which you can see down here. Let me blow this up, maybe this makes this a little bit easier to see, right? The magenta and the cyan lines also describe the exact same plane, right? So this is all the same thing, right? We are all describing the same subspace. So the row space of the matrix A is you can compute it either way, right? You directly get it from the row echelon format of the A matrix, or you look at the column space of A transpose, right? Okay, so that was our row space discussion. Let's go here, and I've written similar code for the column space. So again, all I'm doing is here are the descriptions of the column space. So remember, originally we saw that here C1 and C3, these were the columns of the original A matrix, which correspond to pivots in the reduced matrix, right? So these two vectors should describe the column space of the matrix A. Alternatively, we saw another way you could describe that column space, that same subspace, is by looking at the row space of A transpose, right? That's how we got D1 and D2. And again, all I'm doing is I'm plotting all of these figures, or all of these subspaces as big fat lines, And then we're going to do the exact same thing we did earlier by randomly generating a whole bunch of x vectors and then computing the equation b equals ax, right? So this literally gives us a linear combination of the columns of A for all of these random coefficients or all these random x's, okay? And again, I'm just going to plot those here as blues. Let me go ahead and run the rest of this script, and here is what we end up with. So let me see if I can maybe put all these one next to the other. In fact, I wonder, let me see if I can dock this. Maybe that's the easiest way to do this. Let me see if we can go like this. That way we can highlight things, we can look at things at the same time. So again, here we are. So C1 and C3, right? Again, the green and the red vector. So in this case, you can definitely see the green and the red vectors, right? Here's the green fat vector here, the red fat vector here. Those describe a plane, which is the column space of A. Or we could look at the row space of A transpose to get that same description, and that is the magenta and the cyan lines. And we see all of these describe the exact same plane, and all of these linear combinations of the columns of A are also in this plane. So again, we see this as a nice consistent description, an easy way to visualize what the column space of a matrix is doing, right? Yeah, I think that's probably good. Let me spin this around a couple of times just so everyone can see that yes, this is indeed correct. All these vectors are lying in this two-dimensional plane, which is a subspace of the larger three-dimensional space. All right, so all of this discussion has been talking about linear combinations of vectors. So that leads to the discussion of linear independence. So let's consider this equation here. On the left side you see is just nothing more than what we've been talking about earlier. It's a linear combination of a bunch of vectors like A1, A2, all the way to AM, right? That's all this is, right? Now what we're interested in asking is there some magic number of coefficients C1, C2, Cm, those values that would make this linear combination equal to 0, right? A whole vector of zeros, right? So if the only solution to this equation is if all of these coefficients are all 0, if that's the only solution, what this means is that we refer to this set of vectors A1, A2, Am, those are referred to as linearly independent, meaning that they are not linear combinations of one another. There's no repeat, so to speak, if you want to think about it that way, right? So again, if the only way you solve this equation is by making all these coefficients 0, then all of these vectors, A1, A2 to Am, are called Li, or linearly independent, right? Let's ask ourselves, well, what if that's not the case, right? What if there is some combination of coefficients of these scalars, C1 to Cm, that are non-zero, okay? In fact, let's take a look, and maybe there's one of these that are non-zero. Let's denote this non-zero coefficient as Cp, okay? If one of these C's, like Cp, is non-zero, what I'm going to do is I can shove everything else to the right, to the other side of the equation, and basically solve for the vector which is in front of Cp. That's what I end up with right here, right? So again, all I'm doing is I'm moving everything over to the right and then dividing both sides by this non-zero coefficient Cp, right? So you end up with this equation. And if you look at this and ask yourself about what this means, what it does is it basically says that this vector AP here, right? This can be written as a linear combination of some of these other existing vectors A1 to Am. So again, it's saying that AP can be written as a linear combination of the other vectors, therefore meaning this is AP, this vector is somewhat redundant, right? In the sense that it's nothing more than, it's not adding any new information, right? It's just a linear combination of some of the other existing vectors. So if you're in this case, right, you now have a situation where these vectors are linearly dependent. One or more of the vectors are sort of a repeat or extraneous or basically giving you the exact same information that some of the other vectors are giving us, right? So what's interesting about this is if you think about this long enough and how this relates to our earlier discussion of the row space and the column space, remember, where did we get the row space and the column space of the matrix A, right? We got that by basically performing elementary row operations, and they derive from a reduced from basically an echelon format of the matrix A, right? And we saw in our earlier video on elementary row operations that by construction and by definition, when you create a reduced row echelon form or a row echelon form of the matrix, the non-zero rows are guaranteed to be, in fact, linearly independent because they point in different directions, right? You get that triangular format so that the non-zero rows, they can't point in the same direction because each row above it adds or points in another given dimension. So long story short, this whole discussion is basically saying that if somebody gives you a matrix A and you chop it up in either rows or column vectors, doesn't matter, right? That matrix A is not guaranteed to be linearly independent, right? However, when you look at the row space and the column space, because they derive from a reduced or from an echelon form of that matrix, these row and column space are guaranteed to be built up of linearly independent vectors, right? That's why we call them a basis for these spaces, because it is the smallest set of vectors which can describe this space, meaning that all of these vectors are linearly independent of one another, right? Okay. This leads to now the discussion of matrix rank, right? Because if we saw that, okay, the matrix A might not have all linearly independent rows or columns, some of these might be redundant, right? So let's talk about this. So let's define the column rank as basically the maximum number of linearly independent columns of A, okay? And similarly, let's define the row rank as the maximum number of linearly independent rows of A. Now, what's interesting, right, and you kind of got a flavor for this earlier when we were discussing the row space and the column space, they're basically the same thing. These two, the proof of this statement is maybe outside the concept of this discussion right now, but the column rank for a matrix A is always equal to the row rank of the matrix A. Therefore, a lot of times people just call it the rank. There's not a row or a column rank, there's just the rank of the matrix. And the rank of the matrix is basically measuring the maximum number, or it's the number of linearly independent rows or columns that are in that matrix, right? So the rank gives you an idea of sort of the degenerateness or the repeatedness of rows or columns in that matrix, right? Okay, so with that being said, there's a couple of interesting properties that fall out of this, right? So the rank of this matrix A, right? The easy way to get this, we just saw, is, okay, reduce that matrix to an echelon form. That allows you to very easily compute the row space or the column space, right? And the dimension of the row space or the column space, that is basically the number of linearly independent vectors in those spaces that are needed to describe that space. So the rank of the matrix A, it's basically the dimension of the row or the column space. So in our previous example earlier, we saw that the matrix A was a 3 by 3 matrix, right? But the row space and the column space was actually only two-dimensional, right? It just was a plane, right? So in that case, the rank of that matrix A was 2, because there were only two linearly independent vectors needed to describe either the row space or the column space of that matrix, right? We also saw that, okay, the other way that you can maybe even get this even easier, right? The rank of A, it's you just count the number of the pivots that are in any echelon form of A, right? That's basically how we're getting this row and column space. So if you don't actually need the description of the space, you just need to know how many vectors are needed. You don't need the actual vector values. You can just go ahead and count the number of pivots, right? And again, we see that, okay, what we're really talking about, what the matrix or the rank of A is, it's telling you the number of linearly independent rows or columns inside that matrix, right? This fourth bullet here we kind of touched on earlier, right? We saw that elementary row operations do not change the fundamental row nature of a matrix, right? So row equivalent matrices, they've got the same rank. So if you have a matrix and all you do on that matrix to manipulate it is perform an elementary row operations, you do not change the rank of the matrix, right? And then lastly here, the rank of a matrix A, it's got to be less than the dimension of either the minimum number of the rows or the columns, right? So if you have a m by n matrix, the most rank you can have is the smaller number of the row or the columns. That's basically what we end up with. So that being said, I think this is probably a good spot to leave it. We're going to have future discussions talking a little bit more about what these row and column spaces do and how they're helpful. But let's leave that for another discussion. So right now, I think this is a good spot to leave it. I hope you enjoyed the video. And if so, I also hope you'll consider subscribing to the channel. If you scroll down and click on that subscribe button, it helps me continue making these videos. And the new videos come out every Monday. So I hope I'll catch you at one of these future discussions and we can all learn something new together. So until then, I think I'm going to sign off. Talk to you later. Bye.